right? Now this is theoretical inputs or unbounded inputs. Now we just see the theoretical inputs or unbounded inputs. Another category of theoretical inputs are unbounded inputs. Then we just covered ramp input, parabolic input. Then there is one more input which is also available, and that is the best input for all the theoretical or mathematical calculations. I think that input is also very famous, very familiar to you, and that is nothing but, then another theoretical input is nothing but impulse input. Impulse input. Now this is one of the reference input, which is an impulse input. Then when I am asking the impulse existing at, you are all saying impulse is existing at the impulse is existing at origin. You are saying the impulse is existing at origin. Now delta of t, which is equal to 1 when t equal to 0, which is equal to 0 when t is not equal to 0. Then see here, then what is the meaning of that? This is nothing but, this impulse function is nothing but, now I just take a simple example here, you can easily understand. Now this is a rectangular pulse. This is a rectangular pulse of this pulse width is some 10 units, of this pulse height or amplitude is 0.1. What is the area of this rectangular? Now the area of this rectangular pulse, now this pulse width is 10 and this pulse height or amplitude is 0.1. Therefore this area is nothing but, now this is 10 into 0.1, which is equal to 1. Then now what I am doing is, now this rectangular pulse width 10, now I am reducing. Now this rectangular pulse of width 10 is now I am reducing to, let us say 0.1. Now this rectangular pulse width 10, initially 10, then that is reduced to 0.1. Now this height or amplitude, which is equal to, let us say this is 10, then I am reducing the pulse width, then this height or amplitude is increasing. Then what about this area? Then further what I am doing is, again I am reducing this pulse width 0.1 to 0.01 and this height or amplitude, which is equal to 100. Then I am reducing this pulse width 10 to 0.1, 0.1 to 0.01. Then this height or amplitude is increasing and this area which you observed now will be same, which is equal to unity. Then what is your observation here? Then this rectangular pulse width is reduced. When this rectangular pulse width is 10, 0.1, 0.1, then this rectangular pulse width is reduced. This height or amplitude is increasing. Now the question is, now this is a rectangular pulse width. This is a rectangular pulse whose pulse width now this is a rectangular pulse whose pulse width is tends to 0. Then what happened? Initially 10, 0.1, 0.1, now decreasing, and this rectangular pulse width is tends to 0, and this height or amplitude, is tends to infinity. But what about the area? This is the area which is always 1. Then which is nothing but, then whatever the rectangular pulse I am explaining, if you observe here, now initially this is the rectangular pulse. Now this is the rectangular pulse. Now this is the rectangular pulse. When the rectangular pulse width is decreasing, when the rectangular pulse width is decreases and it is decreases to 0 and its height or amplitude is increasing. That rectangular pulse is nothing but, whatever the rectangular pulse I am explaining, that is nothing but an impulse function only. Then you read this statement. Impulse is a rectangular pulse. Impulse is a rectangular pulse whose pulse width is 0 and its height or amplitude is infinity and the area equal to 1. Therefore, this impulse, that is the reason why you are saying always the impulse is existing at origin, impulse is existing at origin. Why? Because at origin this pulse width is, at origin the width of the pulse, at origin this pulse width is equal to 0. That's why, can you see a rectangular pulse whose pulse width is equal to 0? That we cannot see. The practically does not existing a rectangular pulse whose pulse width is 0, which we cannot detect, which we cannot see. That's why this does not existing practically, but this is the best input for all theoretical mathematical calculations. The reason behind that is, this is a pulse width equals 0, then this 1 is nothing but area under the impulse function. This 1 is nothing but area. This is the area. This is not an amplitude. This is not the magnitude. This is area under the impulse function, or the area under the rectangular pulse whose pulse width is 0 or pulse amplitude is infinity. Area under the impulse function. Therefore, now this is one of the reference input which we are using practically. This is the one of the input which are using to test any control system, but this is also does not existing practically, but theoretically, for theoretical calculations, for mathematical calculations, the best input is an impulse input. Note down this. Now see here. Now this is one of the reference input. Now one of the reference input which we are using as impulse input. Therefore, R of S, which is equal to Laplace transformation of R of t, which is equal to Laplace transformation of delta of t, which is equal to, what is Laplace transformation of delta of t? The Laplace transformation of delta of t, which is nothing but integral minus infinity to infinity. R of t is nothing but delta of t e power minus st into dt. Integration means area. What is the area under the impulse function? The area under the impulse function is 1. Therefore, this is equal to 1. Therefore, finally, the Laplace transformation of delta of t, which is equal to 1. Therefore, this is one of the best input. For reference input is an impulse input. If the reference input is an impulse input, then which is nothing but when you give the impulse as a input, if you give the impulse as a input and its response is called as, if it is the impulse input for a system, if you are giving this impulse input for a system, for a control system, now if you give the impulse input for a control system, then this is nothing but impulse response. Impulse response. This is the impulse input which are giving for a control system, then that is nothing but the impulse response. This is nothing but a theoretical response. This is the impulse response, which is a theoretical response. This is theoretical. For theoretical calculations, this is the best input. For theoretical calculations, now the best response is impulse response. Now similarly, that is for theoretical. For practical, you already know that. For practical, now the reference input, which is R of t, which is equal to U of t, which is equal to 1. Unit step input, which is equal to A, nothing but step input. Therefore, what is R of S? R of S, now R of S, which is equal to Laplace transformation of R of t, which is equal to Laplace transformation of U of t, which is equal to integral minus infinity to infinity, but this is U of t, therefore this is for positive value, therefore 0 to infinity, magnitude is 1 e power minus st dt. If you simplify, this is nothing but 1 by s. Therefore, the Laplace transformation of U of t, which is equal to 1 by s, or the Laplace transformation of A, which is equal to A by S. Therefore, this is the input for a control system if you are applying. Now this is the unit step input or a step input. This is a unit step input or a step input. Now for a control system, now this is called as step response or unit step response. Step response or unit step response, and this is called as practical response. This is the practical response. And this is the impulse response, which is nothing but a theoretical response. Now, just summarize, just listen. For practical analysis, the best input is unit step input or step input. For practical analysis, the best input is a unit step input or a step input, and the practical response is nothing but step response or unit step response. This is for practical analysis, practical calculations, practical behavior. For theoretical analysis, for mathematical calculations, for mathematical analysis, the best input, there are so many theoretical input, ramp input, parabolic input and impulse input, but for all theoretical inputs, among the onboard input, the best input, which is nothing but the impulse input. Now this is the impulse input which does not existing practically, only for theoretical calculations. Now the best input is an impulse input, and now this is the impulse input, and for theoretical calculations the best response is impulse response. Therefore this is the impulse response is the theoretical response. For theoretical input is an impulse input. For practical input is a unit step or step input. For the practical response is a step response. Therefore now where you are doing the practical responses or practical analysis, apply the unit step or step input, see the unit step or step response. For all theoretical calculations or mathematical calculations, then the best one is impulse input and the best response is the impulse response. Okay, so these are the different types of, now what we covered so far is the different types of inputs and different types of tested signals. Now the first point is clear. What are the different types of inputs available? What are the practical inputs? What are the theoretical inputs which we are completed? Now we go to the next step. Once if we know the input, then we want to take any one of those inputs what we are studied and apply to a control system, and we will see the control system response, and from that response we will see the control system stability, then such that then that process will be completed. Then before that you just take this one. Okay, now is it clear? Now these are the different types of inputs, and what are the practical input, what are the theoretical input, what are the onboard inputs available, and which is preferable, which is not preferable, which is for practical purpose and which is for theoretical purpose. So this is different types of inputs and different types of tested signals. What are the practical and theoretical inputs which we are covered. So then we know the system parameters are nothing but system gain and time constant. Then before we utilize these inputs and all these things, then first we will try to find how to find the system parameters. What are one of the system parameters is system time constant. Then how to find that system time constant, then I want to take it. Then in our workbook, question number 3, in our workbook, question number 3, by considering the closed loop control system, transfer function, C of s by r of s, which is equal to s plus 1 by s plus 2, find system time constant. This is question number 3 in our workbook. Question number 3. Then just think about how to find that system time constant. What are the parameters considered for finding the system time constant? Then how to find the answer? Then this is question number 3. By considering the closed loop control system, find system time constant tau. Then now the solution for this is, now what is given? The given one is, this is the closed loop control system. Therefore, this is closed loop 0 and this is closed loop pole. This is closed loop 0 and this is closed loop pole. Why not? One closed loop 0, one closed loop pole. Then what I am saying here is, then I want to give one small concept here. Now you see here, what is the definition of 0? Which we already find in the first session. What is the definition of 0? In the first session, now the 0, which is a reciprocal of system time constant. This is a reciprocal of system time constant. This is a function of time constant. Am I right or not? 0, which is a root of numerator polynomial, which is a negative of reciprocal of system time constant, which is a function of 0, which is a negative of reciprocal of system time constant, which is a function of time constant and makes the transfer function 0. Now this is a 0, which is nothing but reciprocal of system time constant. Am I right or not? A root of a numerator polynomial, which is a negative of reciprocal of system time constant. From here, can I write like this? What is the time constant? Time constant, which is nothing but negative of reciprocal of 0. Now this time constant will make the transfer function, 0. This time constant will make the transfer function 0, which we already know that. Now in the same thing here, now what is the definition of pole? The same. Pole is a root of denominator polynomial. The pole, which is a root of denominator polynomial, which is a function of system time constant. This is also a function of time constant. This is also a function of time constant. then the system time constant, which is nothing but negative of reciprocal of pole, and this fellow will make the system transfer function how much? Infinity. You know this concept. What is the definition of zero? What is the definition of pole? Now this is a pole definition, which is a function of system time constant, which is a negative of reciprocal of system time constant, which makes the transfer function infinity. And this is a pole which is a negative of reciprocal of system time constant. A zero is the root of numerator polynomial. Pole is the root of numerator polynomial. Both are function of time constant. Both are function of time constant. And this time constant is a function of zero. This time constant is a function of pole. But this time constant will make the transfer function zero, and this time constant will make the transfer function infinity. Then you just compare these two and you tell me whose effect is more on the performance of the control system. Whose effect is more on the performance of the control system? One fellow will make the transfer function zero, another fellow will make the transfer function infinity. Then you can think about whose effect is more on the performance of the control system. Control system means control system complete behavior is available in the transfer function. Therefore, this zero will make the transfer function zero, but this pole will make the transfer function infinity. Therefore, a pole effect is more on the performance of the control system. Therefore, while calculating the system time constant, we consider the poles. We don't consider the zeros. While calculating the system time constant, we consider the poles. Not only that, in the previous sessions which we are finding characteristic equations, there itself I am saying, what is the meaning of characteristic equation? The characteristic equation will give everything, will give complete characteristics. The complete characteristics is nothing but system time constant and gain everything. So the system time constant is given by characteristic equation. Then you just think about what is there in the characteristic equation. Characteristic equation consisting of zeros or characteristic equation consisting of poles? The characteristic equation always consisting of poles. This is closed loop zeros and this is closed loop pole. Therefore, the characteristic equation consisting of closed loop pole, therefore the system time constant which we are finding only from the pole's location only. Therefore, the time constant which we are finding only from the pole's location. Therefore, from this particular comparison, then what we will finding is then what is the time constant? Now tell me from here what is the definition of time constant? Now the time constant which is nothing but, now see here, the time constant which is nothing but negative of reciprocal of pole. The time constant is nothing but negative of reciprocal of pole. This is the time constant definition now. But pole, yes, S means there are two parts. What is two parts? Then the S which is nothing but sigma plus j omega. S which is nothing but sigma plus j omega. This is the real part and this is the imaginary part. Therefore, this is pole. P means pole. This is pole real part and this is pole imaginary part. Then now what I am saying is, now this is the time constant which is nothing but negative of reciprocal of pole, and a pole which is having a real part and imaginary part. Now what I am saying is, this is the real part of pole and this is imaginary part of pole. Now this real part is having some significance. This imaginary part is also having some significance. Then, sir, what is the real part? Then the real part saying what? What is imaginary part? What is imaginary part is saying? Then this pole is having, it may be having a real part and it may be having an imaginary part. Sometimes it is having both, not a problem. But what the real part will give, what type of information the real part is given to you, and what type of information the imaginary part is saying to us, right? What is the significance of that real part? What is the significance of that imaginary part? We will see. Then this real part will saying what? This imaginary part is giving what? Now first we will see this one. The imaginary part will gives directly the frequency of oscillations. The frequency of oscillations. The name itself omega, no? This is omega, the frequency of oscillations, which is nothing but units are omega units, radians per second. The frequency of oscillations present in the response. This is the significance of omega. What omega is saying is, listen carefully, the omega is giving directly whatever may be omega. Let us say this J3 means omega equal to 3 radians per second. What is the meaning of that? If omega is 3, j omega J3, omega equal to 3 radians per second, which means that in the response, what is the meaning of response? After applying the input, you can get the output. That output is nothing but this response. In that response, is there any oscillations? Is there any sine wave? Is there any cos wave? Is there any frequency of oscillations? That frequency of oscillation is directly given by this imaginary part. There is no need to apply the input. There is no need to see the response. You can find directly in the response, is there any oscillations existing? In the response, is there any sine or cos wave is presenting? In the response, is there any sinusoidal oscillations are present or not? You can identify directly without applying input, without looking the response, by looking the imaginary part of the pole. Whatever the imaginary part of the pole is saying, that should be the frequency of oscillations present in the response. Some of you are saying is, sir, if there is no imaginary part, sir, if there is no imaginary part means j omega is 0, no imaginary part. Omega is 0 radians per second, which means what? When omega equal to 0 radians per second, which means in the response, in the output, there is no oscillations. There is no oscillations present in the response. Based on the imaginary part, you can give that particular statement, not an issue. Sir, who says that is correct? Sir, that is correct or not? I am not guaranteed, sir. I have some confusion. This imaginary part is saying and the response is presenting, both are matching or not, that we will check, not a problem. Okay, then we will take one simple problem and we will find the frequency from the imaginary part and we will see the response. Now in the response and imaginary part saying both are matching or not, we will see. Okay, right. And that is the story about the imaginary part. That is the significance of the imaginary part. Sir, what about the real part? What is the real part is giving? The real part will give what type of information to us? Now, this is the real part. From the real part, we want to calculate. From the real part, we want to calculate system time constant. From the real part, see here two definitions you just clearly understand. Imaginary part will give directly, but some of you are thinking imaginary part will give time constant. No, not at all correct. So I am not writing like that. No, from the real part, we want to calculate system time constant. So for finding the system time constant, which part is useful? Real part. For finding the frequency of oscillations in the response, which part is useful? Imaginary part. That 2 points you remember in your mind. Okay. From the real part value will be useful for finding the time constant, and the imaginary part will directly give the response having any oscillations or not. Okay. Therefore, now you tell me from here, for finding the system time constant, we consider only poles because characteristics are coming only from the poles, not from the zeros. Therefore, what is the time constant definition? Time constant is nothing but negative of reciprocal of pole. There we will stop. Here we will stop. Then the pole is nothing but is having real part and imaginary part. Now you tell me which part I want to consider. I want to consider real part or imaginary part? Yes, then I want to consider real part, because for finding the system time constant, we can utilize the real part. Therefore, what is the time constant definition? The time constant, which is nothing but negative of reciprocal of pole. In pole, which part? Real part. Therefore, this is nothing but the time constant, which is nothing but negative of reciprocal of pole real part. Therefore, real part of pole. Real part of pole. So this is the time constant definition, and that is your question, what he is asking. This is what he is asking. Don't think like a question. See, in the classroom, what we are doing is, sir, this is question, this is solution, this is question, this is solution. Don't go for that particular method. I am not interested on that particular method. Now, one question, one solution, one question, one solution is not at all useful to you. Now, what you are identifying, why you take a question and go to the solution, then in between there should be a gap. This is question, this is solution. Now, while solving this question and go to the solution part, in between, in this particular length, you learn some concept, you learn some knowledge, you gain some concept, you gain some basics. Now, such that that concept which is useful not only this particular question, for any question this particular concept is useful. This is the question, but I am not giving a solution immediately. For finding the solution, then we have this particular concept, and you have some particular parameters and knowledge and all these things. Okay, so finally I think now you have the solution for this particular question. Then what is the solution for this particular question? Tell me now. By considering the closed loop control system trans function, find system time constant. Briefly I am explaining. Listen, find system time constant. Then what I am doing is one closed loop 0, one closed loop pole, one closed loop 0, one closed loop pole. But closed loop 0, closed loop pole, both are function of time constant. Both are function of time constant. Therefore, time constant is also function of 0. Time constant is also function of pole. But you already have an experience that this 0 will make the trans function 0, but this pole will make the trans function infinity. Therefore, the pole effect is more on the performance of the control system. Therefore, while finding the system time constant, we consider the pole. And you already know that the characteristic equation is nothing but characteristics it will give. The characteristics is nothing but time constant, gain, all these things comes under characteristics. But so the characteristic equation consisting of what? The characteristic equation consisting of only closed loop poles. Therefore, the time constant is obtained from the closed loop poles itself. But for finding the time constant, here there is a confusion. The pole means, S means real part and imaginary part. Pole is having a real part, or pole is also having a imaginary part. Therefore, real part is having this significance and imaginary part is having this significance. Imaginary part is finding frequency of oscillation. From the real part, we want to find the system time constant. Therefore, the definition of system time constant is nothing but negative of reciprocal of real part of pole. Real part of pole. Therefore, then what is the system time constant? Now here is the question. Now what is the system time constant? Now the system time constant solution is negative of reciprocal of real part of, not 0, real part of pole. What is the real part of pole? The real part of pole is, this is on the real axis. Therefore, the real part of pole is -2. Minus cancel, which is equal to 1/2, which is equal to 0.5 seconds is the solution for this particular question. But for finding the question and finding the solution, which is very simple, only one step, but for getting this one step, you have to understand this total concept. Okay, take this question, and now you have one important parameter of the control system is nothing but control system time constant and its definition. Why you are not taking 0, why you are taking pole, what is the significance of real part, what is the significance of imaginary part. This is the real part of pole and this is the imaginary part of pole. Take this one. Okay. Now see here. Now this is a very good concept which is useful throughout our subject. Now because one of the system parameter is nothing but the system time constant, which is nothing but negative of reciprocal of real part of the pole. Okay. Yes. Now this is question number 3 and this is a solution in our workbook. So this particular you just remember, real part of the pole is giving what? Imaginary part of the pole will give is what? Okay. Real part of the pole, from the real part of the pole we want to calculate the time constant. From the imaginary part of the pole we'll use directly the frequency of oscillation. Now we will see. Now where we are starting is inputs, different types of inputs which we are already completed. Then what is the purpose of inputs? Once if you have the inputs, you can easily up the inputs and see the response. Once if you have the response, this is the actual cycle, right? Once we have the response, from the response we can decide the stability. This is the concept actually we are doing, right? Stability means that control system is good or not. This is the cycle. For that what we are doing so far is, what are the different types of inputs, what are the practical inputs, what are the theoretical inputs which we are doing. Now this is input. What are the theoretical practical inputs? Now we will finish this. We know this. Okay. Now we know what are the different types of inputs available which we are finished. Then once if you know the input, then you apply that input and see the response. We want to see the response. Once if you see the response, now from the response, from the output, you can easily decide the system stability. That is actually the final concept, am I not? So what are the different types of inputs available? Now I know that. Then apply that input and see the response. Once if I get the response means outcome, output, behavior. Now from that behavior, from that output, I can decide that system is good or not. The system is good. Now that system is stable or unstable, we can easily identify it. Okay. So now in this particular cycle, we finished this particular part, right? Now what are the different types of inputs available and what are the different types of theoretical practical input? Now this is completed. Then we will switch over the second part and the third part. So for finding this, then I am giving one question in our workbook. Based on that, we will try to finish this concept and as well as that particular question. Now in the question number, even our workbook, question number 4, problem number 4 in our workbook. In our workbook, question number 4. Now see here, in our workbook, the question number 4 is what? By considering the closed loop control system C of S by R of S, which is equal to S plus 1 by S plus 2 into S plus 3. Now the question number 4 is by considering the closed loop control system transformation C of S by R of S, which is equal to S plus 1 by S plus 2 into S plus 3. Now what he is asking is, I just give an overview. Question is find system time constant and find frequency of oscillations present in the response and find order and find time constant, find frequency of oscillation, find order, draw the response in time domain, draw the response in time domain, and find and decided system stability. This is the question. There is no need to take this question, that is already there in your workbook. Okay, question number 4. You just observe this question. Why I am writing this question is, you just observe. What he is asking. Just read the question. By considering the closed loop control system, find time constant, frequency of oscillations, order, draw the response in time domain, and decided the system stability. In this question itself, I am trying to explain this particular cycle. You observed or not? Now what is the cycle? Now what is the question? Draw the response. Response means output. How you can get the response? How you can get the output? The response or output is coming only when you are applying some input. The response is coming, output is coming only when we are giving some input. That's what I start with the first part, input, which we already finished. What are the different types of input? What are the theoretical inputs? What are the practical inputs? What are the available inputs? Then which we are already finished. Therefore, we will take any one of that particular input what we are finished. Then that input, if you apply to this particular control system, then you can get the response. Once if you get the response, now from the response what he is asking, from the response we want to decide at the system stability. See here, from the response we want to decide at the system stability. Therefore, whatever this cycle, it should be totally covered in this particular question. Whatever the cycle, whatever we are having some concept, no, input, response and stability, the same way we are giving here. Okay. Now we will trying to find first a simple, in this particular group of parameters, then some parameters which are directly identified, then that parameters you tell me. What are the parameters you can easily finding? See here. Now these are the poles location. Then first you locate the poles and zeros for any question is given, such that it is very easy for you to get the answer. Once if the question is given, first you locate the poles and zeros and explain, such that you have some concept, such that your analysis is also very easy. Now this is explain. Now s plus 1 equal to 0, s equal to minus 1, that's what I am saying already previously. See the real part. If the real part is negative, come to the left hand side. If the real part is positive, come to the right hand side. S plus 1 equal to 0, s equal to minus 1, s equal to minus 1 is a 0. S plus 2 equal to 0, s equal to minus 3. Sorry, s plus 2 equal to 0, s equal to minus 2 is a pole. S plus 3 equal to 0, s equal to minus 3 is a pole. This is closed loop 0. This is closed loop pole. This is closed loop pole. Then while looking this, how many closed loop poles? How many closed loop poles here? This is one closed loop pole. This is one closed loop pole. Total 2 closed loop poles. If there is 2 closed loop poles, therefore you can easily find order. What is order? There are 2 closed loop poles here. 2 closed loop poles. Therefore, order which is equal to 2 directly. 2 closed loop poles, therefore order equal to directly 2. Then one question is over or not? Order is completed. Then now next one is time constant. What is the time constant? For just now we have one formula for finding the time constant. You want to consider 0 or you want to consider poles? For finding the system time constant, we consider only poles. We don't consider zeros. We consider only poles. But what happened here? Time constant is nothing but negative of reciprocal of real part of pole. Real part of pole is -2. And similarly, time constant is nothing but negative of reciprocal of real part of pole. What is the real part of pole? -3. Therefore, time constant is nothing but 0.5 seconds. Time constant is nothing but 0.33 seconds. Therefore, the time constant is 0.5 seconds. The time constant is 0.33 seconds. But what is the problem here? Then with the previous basic formula, whatever we are finding from this, we have how many time constants? We have two time constants. One is 0.5 seconds, another one is 0.33 seconds. But we have two time constants here. We have two time constants here, but the control system will have only, we have two time constants here, but the control system will have only one time constant. Now we have two time constants here. We have two time constants, but the control system will have only single time constant, only one time constant. So what we have to do for that? But in the previous concept, negative of reciprocal of real part of the pole is a correct formula? No. Then why you consider that particular formula is correct? Yes, in the previous problem it is correct because the time constant is nothing but negative of reciprocal of real part of the pole. If the transfer function consisting of a single pole, that particular formula is correct. But here the transfer function consisting of more number of poles, not a single pole, more than one pole. If it is a more than one pole, now whatever the formula we are taking previously is not matching here. Therefore, we want to find what should be the standard formula for the system time constant for any number of poles. Therefore, now this is somewhat not clear here. We have two time constant, but the control system will have only one time constant. For that, what we have to do it, we will see. Okay, we will see for what we have to do it. Therefore, this is order, only one parameter is coming. No, time constant is not like this. We have to go for another formula. What is that formula? How it will come? We will see, and we will continue the question in the next session. Okay, now you first take these two, and only one parameter we are finding order, and the remaining parameters we will this question will be continue in the next session. Thank you.